Good evening, everyone. Thank you for joining us for our Caltech Astronomy Stargazing lecture. I'm Dr. Cameron Hummels. I will be your MC for this evening's event. We've got great observing conditions outside. I don't know if you noticed when you drove in or walked in, we've got really clear skies. So hopefully the stargazing component of the evening after our presentation is full of wonderful views of the sky through our telescopes. So I'll just lay out what our schedule is for tonight with a few announcements. So I'll have a few announcements and then I'll introduce our speaker who's going to talk all about galaxies, the full picture of galaxies that maybe some of you are familiar with certain aspects of, but he's really going to cover the whole aspect of it. That'll last about 30 minutes and then we'll have a brief Q&A with all of you, followed by kind of a split where we will continue in this room with a Q&A panel consisting of our speaker, myself, and two other professional astronomers to answer your questions about astronomy and physics and space science on whatever topics you might want to ask. But at the same time as that, as I mentioned, we'll have telescopes operating with astronomers out on the athletic fields just behind this building. And for that, you'll just walk out the front door and follow the signs, and it's about a minute walk to get there. And there are 3 telescopes that'll be set up tonight, looking at the moon, various craters and such on the moon, looking at Jupiter and its brightest moons, and then also looking at deep sky objects like galaxies and nebulae and star clusters. So it should be great. One thing that's nice about this is you can go out and look through the telescopes and then you can come back in to ask your questions or vice versa. Both of those will be going on until about 9:45. So there's plenty of time to peruse the telescopes or if you're just like, no, I'm done, I want to go to sleep, then you can also, it's a free country. You can do that as well. These events are live streamed. Hi, YouTube audience. We're also on YouTube right now. So if you want to catch this later and show your mom all the great stuff that you learned here, you can go to our Caltech Astronomy YouTube channel and watch this lecture again. We also have something like 200 lectures over the last 10 years on that channel on various different astronomical topics, from black holes to galaxies to the search for life in the universe, that you can peruse. So I encourage you to check that out if you're interested. Other announcements. Last night we had our first Altadena stargazing night, just a few miles from here for the community. And the conditions weren't as good as they are tonight for observing. It actually rained about 30 minutes before we got started, but in the end it did clear up and we did have some decent views through the telescope. So that was a few hundred people came out to that, which was great. We hope to do that again, potentially in the fall, at that same location. So stay tuned for future events like that. These lectures take place once a month on a Friday night and follow the same format: a presentation given by a professional scientist on an astronomical topic, followed by telescopes and the Q&A panel. Our next one will be Friday, June 6th, and it'll be all about space weather. So much like our Earth has weather, space has weather. Primarily, at least in our solar system, it's caused by material that's being flung off or radiation that's coming off the surface of the sun, and it affects things here in terms of causing the northern lights and potentially causing problems with our electrical grids and such. So our next speaker, Ivy Davis, is going to be talking about that in a month's time. We also have another series of events called the Astronomy on Tap activities that take place at a bar in Old Town Pasadena, just a few miles from here, the Doghouse Beer Garden. Even though it is a beer garden, it's outdoors and it's open to all ages, so families can come. And that event is a little bit less formal than these. It consists of 2 15-minute presentations by scientists, again, at a public level, like you'll have tonight. But there's also live music, and there's astronomy-themed pub trivia, and it's quite fun. But those are on Monday nights. And our next one of those will be a week from this coming Monday, on May 12th, Monday, May 12th. And the 2 speakers will be talking about the search for dark matter, this kind of unseen, we don't know a huge amount about it, aside from its gravitational influence on things that we can see. And the other speaker will be talking about observing the universe in gravitational waves using instruments like the LIGO instrument that recently got the Nobel Prize and other planned instruments to see this ripple in space-time in ways that we can't necessarily see things with visible light or other wavelengths of light. So I hope you'll join us for that. There's one more event happening at the end of this month, May 25th. Pasadena has this is Pasadena's month of bicycling, and there's going to be a space ride that takes place where people meet here at Caltech, just a few feet from here, and I'll give a 20-minute or so presentation outdoors, no presentation, no slides or anything like that, outdoors, about the history of Caltech and its role in the development of astronomy over the 20th and 21st century, and some of the cool discoveries that have been made by people here. And then a group of 40 or 50 or so of us will bicycle to the Planetary Society, NASA Jet Propulsion Laboratory, and Carnegie Observatories, which also, all of those have played major roles in the development of astronomy and our knowledge about the universe over the last 100 years. And at each location, one of the scientists in that spot will give a short presentation. Again, not slides or anything, just orally a presentation at that location. And it'll take a few hours. So if you're interested, I posted a bit about this last week on our social media. If you look up Pasadena Space Ride, you can find more information. And you do have to sign up, although it's free. They just don't want it to turn into like 1,000 people trying to bicycle between the various spots. So that should be pretty fun. I think those are my announcements. I've one final important announcement, and that is these events, what you're going to hear about tonight, and what you've heard about at all of our previous events, is science that's done through the support of taxpayer dollars. The science that Evan's going to discuss, or the science that happened that we discussed last week, all of the science that you see at these events or read about in the newspaper is funded through grants from NASA or the National Science Foundation or various different federal branches that fund science that wouldn't otherwise be funded. And part of the reason for this series is to try and share the insights that we figure out about the universe with all of you, who ultimately are our bosses as taxpayers. But the new administration put out their proposed budget for the next fiscal year. And in that, they did that today. And right now, there are major cuts to federal funding of science, including the National Science Foundation cut by over 50%, NASA cut by something like 30%. And I don't want to get political, and I don't want to get into the details of this. I just want people to know that the result of that, if it goes through as it is, will be pretty horrific for science in the United States. Certainly, these events, these lectures will stop. I won't have a job. Many other people in the fields of science won't have jobs. And in fact, all the science that we talk about or that you read about in the newspaper will just stop happening in the United States largely. It might continue in China or maybe at some level in Europe, but it's really going to be catastrophic for science. So if you feel strongly on this issue, I encourage you to reach out to your representatives, senators in California, or if you're on YouTube, senators and Congress people, to express your opinion to potentially oppose these cuts, because it really is going to be like the end of science in the United States. I'm not trying to mince words. It's going to be really bad. So anyway, continuing on, we'll celebrate the science that we have done. Our speaker for tonight grew up nearby in Carson, California. He started actually at community college. He went to El Camino Community College before then finishing his undergraduate degree at Cal Poly Pomona, just a few minutes down Highway Interstate 210. And then he joined Caltech as a graduate student these last few years. And he's actually defending his PhD in just 3 weeks' time, 3 weeks from today. And when he finishes, he will begin a really prestigious fellowship, postdoctoral fellowship at UCLA, later then moving to Carnegie Observatories in Princeton, doing some of the stuff that he's going to talk about tonight. He is a world expert in the observational studies of galaxies and the components of galaxies, and and it really influences my own research. So I'm very grateful to him and his team. But please welcome our speaker for tonight, almost Dr. Evan Nuñez.
Thank you very much for the warm introduction, Cameron. And it is very, very nice to be here with you all. We have a pretty cool talk lined up. I actually had a lot of fun making it. It's actually pretty ambitious, so it'll go a little bit quickly, which I do apologize for in advance. But what I want to try and do is lay from the observational perspective, right? Like from the actual data that we collect from the night sky, how we know that there are multiple parts to the galactic ecosystem and how important those parts are to the future evolution of our galaxy. And for me, it's all about homecoming and how we can understand how our galaxy formed and how we ended up getting here today so that we can have this hopefully interesting talk tonight. So Cameron actually did a fantastic job talking a little bit about me. So I'm going to go through these slides a little bit quickly. Born and raised in Southern California. All my family's from Compton. I grew up in both Carson and Torrance. So Southern California to the core. And there's a lot of amazing astronomy that I'm so thankful that I had access to as a young buck, as they say, as a young kid. For me, family is everything. I don't think I'd be standing here in front of you if it wasn't for the amazing support that I've gotten from my family all of these years, especially my mom, my grandma. As Cameron mentioned, my undergraduate was sort of split into two parts: El Camino College, about 45 minutes down the freeway, and then Cal Poly Pomona, where I got my bachelor's in physics and with a specialization in astrophysics. As an undergraduate, this is for those who are going to be going to college soon, I ended up doing three summer internships that were actually funded by the National Science Foundation. So what Cameron was talking about is very important, very significant. As a matter of fact, my student this year, she unfortunately didn't have the opportunity to get RUs because a lot of the ones that she applied for got canceled. RU, by the way, stands for Research Experience for Undergraduates. And this is a great way to sort of get your feet in the water for what research actually looks like. So I spent time at the University of Wyoming, about 10 weeks, great summer. Cal Poly Pomona, which resulted in the first paper that I ever ended up writing, many years later. And then my final experience was at Harvard, the Harvard Smithsonian Center for Astrophysics, the Smithsonian Astrophysical Observatory. Fantastic time. So for fun, I'm a console gamer. I have not quite made it over to PC yet, but I have basically every new generation console: Switch, PS5, Xbox Series S. I'm a big music fan: jazz, rap, hip hop, indie alternative, shoegaze, all the fun, anything that just sounds and feels good. I'm also an amateur photographer, as well as a pretty big sports fan. I actually played football all 4 years in high school, and I'm currently now playing a little more basketball, as well as trying to run a little bit more. I ran the Pasadena half a few years ago, and I'm trying to get back to that. So anyways, I want to get on my soapbox for about one more minute here, and I want to make this argument that the deeply personal voyage of scientific inquiry must always keep human well-being as a compass. So this is really, I want to pay remembrance to two folks who we lost in the field that meant a lot to me. My former classmate, Jose Flores Velasquez, who who was taken from us during my first year at Caltech. He was a graduate student at UC Irvine, actually also funded by the NSF. Then I have another person I wanted to highlight, Dr. Lisa Townsley, who was an amazing scientist over at Penn State. And actually, if it wasn't for the work that she did in the X-rays, my first paper would not exist. And so the reason I want to highlight them is because they helped teach me that you can both be a good scientist as well as a good person. Be surprised how much ego exists in astronomy, and I have it as my personal mission to bring humility back into the field. So thank you for that. Who has been out to a dark sky before? Show of hands. Fantastic. That actually makes me very happy. For those who have not been, you got to go to Joshua Tree. It's only a 2-hour drive. Fantastic. If you've gone in the summertime, you've probably seen this. This is the Milky Way. This is our galaxy. What this really is the most dense part of our galaxy. And what I want to first do is just build up and have us understand what the different components inside of the galaxy actually look like. The first thing that you'll notice is that there are stars all over the place. And the way that we can sort of extract a little bit of physics about these stars is by looking at their colors. So blue stars are typically younger and more hot, and then yellow and more red stars are cooler and therefore a little bit and also older. The next thing that you'll notice are these dust lanes. And so in this case, dust that is not the same that we would think about in our homes. That most of that is actually dead skin that we have to sort of get rid of. In this case, these dust particles are more like like smoke particles in terms of their size. But what you notice is that they have a pretty significant impact on the light that we can observe from the galaxy and from all these other stars that we see. The next is, if you sort of look at these dark patches in these dark regions, that's actually cold, dense gas that will at some point form stars. And then, of course, we have star-forming complexes that are actually forming stars. So what I want to do is then all of this is held together by what we would call a dark matter halo. So a very, very large halo of dark matter that we have really no idea what it truly is, but it's very, very massive. So that's an important key that I'll talk about a little later on. One thing that I want to note is that I'm being a little bit specific here in the sense that we're looking at the disk of the galaxy, but really what we're seeing here is the interstellar medium of our Milky Way. This is going to be important as I talk about the different parts of galaxies and how this scales up larger. So what I want to do from here now is actually zoom into what star formation actually looks like. And I'm going to make the argument, or really the observation, that star formation has a significant effect on the interstellar medium. So what we're seeing here is an image of the Carina Nebula, which is one of my favorite objects, or one of my favorite star forming regions, because this is actually the first region that I wrote a paper on. What we're looking here is in the infrared. If you want to see what this looks like in the optical, which is the wavelength that we can see with our eyes, just go to the bathroom and you'll actually see a huge mural of this that was taken by Hubble Space Telescope. It's very, very nice. The colors here can be thought of effectively as temperature. So we can see very dense gas on the right here that's cold, and then this more diffuse gas that sort of goes over here to the blue. What I want to note is that normal stars here you actually haven't seen quite, or we don't see them yet because they're still forming. And it turns out that those normal stars are very, very numerous and can actually drive these powerful jets that end up putting a lot of mass back into the interstellar medium. The next are these massive stars. These are the kind of the fun ones to look at, right? So this down here, for those that are familiar, this is the amazing and very famous binary star called Eta Carina. It actually has had outbursts in the past, like in the mid 1800s or so. These stars, there are very few of them, right? They live fast, they die young. They're very, very bright. As a matter of fact, all of this dust and this gas that's being whisked over here, and then all this stuff over here is being carved out primarily by the massive stars that are in these complexes. And the argument that I'm making here is that star formation is not a passive process, right? Again, you have this injection of mass, energy, as well as you have this mechanical pushing of the ISM. What we call that is feedback. And you actually have multiple types of feedback. But again, this talk is already quick, so we'll just focus on what we call stellar feedback. Okay? Now, I say that massive stars live fast and die young. Let's actually show an example of what I mean by that. So this is M1, the Crab Nebula, or for the amateur astronomers that are out there, this is a Messier Object 1. This is a remnant of a core collapse supernova. And I'm going to be showing one of the few times we can actually see real motion in space. And so this is funny enough, actually, a compilation of images taken by an amateur astronomer, I think in Austria. And you can actually see this expansion of this object, right? So again, what we're seeing is actually a stellar explosion that just about every population had seen back in 1054. The Chinese astronomers and a lot of other folks noted it as a guest star. We have always had a very deep connection tie to the sky, so we got a little bit more technologically advanced. The reason I wanted to show this is because this directly shows in the most explicit way that I could argue what I'm trying to say, which is that star formation, as well as massive stars, inject lots of mass, metals, energy, and can end up pushing a lot of gas in the interstellar medium. For those curious, the metals that I'm talking about here in abundance: carbon, oxygen, silicon, sulfur, iron, and nickel. And for those that are also curious, the actual expansion of this, it's something like 9,300 miles per second. So one Mississippi, 9,300 miles, right? It's a lot. It turns out that massive stars and star formation is always clustered. And we actually found out somewhat recently, over the past decade or so, that massive stars typically form in pairs. And those massive stars that are in pairs typically also form in clusters. And when you have enough of these stars, you can actually drive what are called galactic outflows, galactic winds. This is another very famous object called M82, Messier Object 82, or the cigar galaxy, because if you actually look at this through a telescope, it actually looks like a little cigar. And just to break this down here, this is another galaxy, right? Not the Milky Way. So once again, we have the disk or the interstellar medium where you have all of this star formation occurring, and it's driving these galactic outflows. So what we're actually seeing here is ionized hydrogen, so hydrogen that's had one of its electrons ripped off and then recombined later on. what you can notice is that this is actually pretty significant, right? It's like there's a lot of mass that's being ejected. So I want to pose a question to you all that I just want you to think about a little bit. Where does all this gas go? And secondly, does it actually matter? So just ponder that. Where does all this gas go, and will it actually matter for the long-term, health or well-being of the galaxy? I'm going to pivot here a little bit and say that M82 is one of many, many galaxies that we have in the local universe. And I kind of take us back a little bit to 1922, where Edwin Hubble did one of the first sort of extragalactic surveys using the 100-inch Hooker telescope up at Mount Wilson Observatory. Hooker is the last name of I think he was an astronomer, James Hooker, by the way. So what we're seeing here are our elliptical galaxies. And the very beginnings of galactic astronomy were very phenomenological. So in other words, we see a galaxy with this shape and it has light that's similar to this. We see a galaxy that looks like this and it has this color, right? And over time, we ended up moving more from, the sort of postage stamp and taxonomy of galaxies to physically what is going on. And actually, Edwin Hubble himself also tried to do this as well. For those that are curious, by the way, that have keen eyes, this is actually M87. So if you remember that amazing press release that came from the Event Horizon telescope, this is where we actually took a direct image of the supermassive, well, really the dust surrounding a supermassive black hole, which is pretty interesting. So the way that Hubble tried to make sense of what he was seeing was by making what we now call the Hubble tuning fork. So before we even get into this, I want to make it very clear this is not a complete description of galaxies, but it's perfect for this talk so we can get through a little bit and see. So on the left-hand side here, we have very large elliptical galaxies. If you were to actually see these in the sky, they just look like balls, basically look like spheres. And over here, we have the spiral galaxies that we know and love. So we ourselves are in a bar spiral galaxy. What Hubble thought in the beginning was that galaxies go from over here to these spheroids, and they march and they move over in time to becoming spiral galaxies. And this actually isn't an unreasonable thing to think, right? If you have yourself a spherical collapse of a cloud, you would expect that whatever the angular momentum that cloud has as it starts to collapse on itself would actually turn itself into a disk. So it's not unreasonable at all. It turns out, though, that he actually got it exactly wrong. And it's the exact opposite that happens. So spiral galaxies end up using all their gas at some point for whatever reason. This is also an unknown problem. We call it galactic quenching. And over time, very likely, they end up merging with other spiral galaxies to make these giant ellipticals. The reason I like to show this is because even though he got it wrong in like almost the exact opposite way, it's still remarkable to think that galaxies in general follow such strong relations, in the sense that as you move from right over to left, you have strong relations with the age, the color of the galaxy, how much gas is available to form stars in that galaxy, as well as the sort of the stellar mass of this galaxy. And now with the advent of digital surveys, like in the early 2000s, the Sloan Digital Sky Survey, we actually have been able to go and sort of peer into the fine details of this diagram. So as I mentioned before, this is not a complete description, right? It doesn't explain how galaxies evolve in terms of mergers, and how dwarf galaxies exist, different processes of how galaxies interact with their satellites, Ram-Petra stripping, all of that fun stuff. But what we have been able to do is try to account for all the mass that's associated with galaxies. And what we ended up finding was pretty interesting. Where is all of the visible matter that one would expect a galaxy to have? So this is the first plot that I'm going to be showing here that actually looks at real data. As I mentioned earlier in the talk, since I'm an observer, I want to try and show as much real data as possible. On the y-axis here, we're looking at the observed visible mass that we would infer from looking at the light being emitted from the galaxy. And then on the x-axis here, we're looking at the total halo mass of a galaxy, including this dark matter halo. There's a prediction from what we know about from the cosmological parameters that we've been able to pin down from amazing space missions like Planck, for example, that all the galaxies should follow this line here, that there's some fraction ratio of your halo mass that should turn into galaxies, or that should turn, into visible matter. This is where the Milky Way lies. As we can see, none of the colored points actually match the black line. Like in its simplest implementation, that's all I'm basically saying. What you notice, by the way, is that this axis is logarithmic. So every tick mark here is a factor of 10. So this is 10, 100, 1,000, million. or sorry, 10,000. And what we can see is that depending on how low in the mass you go, you can see huge discrepancies between the predicted mass that we would expect versus how much mass we're actually measuring from these galaxies. Another way of saying this is that depending on the mass that you're looking at, galaxies are missing up to 90% of the visible mass that should be there. So what gives? Well, what if the data is just bad? I think that's a very fair question to bring up. Turns out that what we're seeing here is a collection of more than 50,000 galaxies that are basically all averaged over into these individual points. So, and they're all analyzed in basically the similar and in the same way. So it's possible, but very unlikely. Well, did that mass just get ejected somehow? We already showed you evidence that that there are galactic outflows that move mass. I think that's possible. Did the mass never actually enter the disk of the galaxy? If we sort of keep those 2 points in mind, is it just that maybe there's mass that exists that surrounds the galaxy that we just have not detected? So that's a question that we're going to ask. Do we have any evidence for this unseen circumgalactic gas? So let's break down this word, circumgalactic. Circum means you can think about a circumference or surrounding, and then galactic, of course, would be the galaxy. Do we have any gas? Do we have any evidence to show that gas is around, or sorry, that we have extended gas that exists around galaxies? To answer this question, we have to give a incomplete but pretty intuitive explanation of how we actually detect gas around sources. So this is Kirchhoff's laws of spectroscopy. For those that are in the know, this is yes indeed the same Kirchhoff's that for the electric diagrams. So first is that the way that we can get emission is if we have a hot object. So this can be a light bulb or the sun. And what we're seeing here on the y-axis is brightness here as a function of color. So we can see that, this is basically assuming that this object is about as hot as the sun. We can see that it's peaking around the green here. And so we know then that the CGM, or that this circumgalactic medium, can't be hot because we don't actually see it, and it can't be it can't be an object that's similar to the sun and to a light bulb. Well, what we can do next is, if you were to have an object like this that is emitting its own spectrum, and let's say you have some cold gas in front of it, what you would actually end up seeing are these little lines of absorption that, depending on the elements that are inside of that gas cloud, are going to line up at different wavelengths. So, for example, this is, remember that the element I talked, or what I talked about earlier, hydrogen. So this is actually hydrogen alpha. We can see that it's in the red. So this is very good for trying to find cool gas that's low density and extended. The downside here, of course, is that you need to have some object on the other side. So we'll have to keep that in mind. The other alternative is to have the gas itself emit. And typically, at least with the way that Kirchhoff is doing this, you'd actually need that gas to be both hot as well as very dense. And you'd actually have effectively the opposite of this, where you would see emission lines that are the chemical fingerprints of whatever that gas is made of. So in our case, what we want to do then, it's very, again, we don't see this gas. So it's very likely then that it's probably very diffuse and very cold. So what we want to do is try and use this method here in the middle. So the question then is, do we have any evidence, towards these, these very bright objects that we actually see this circumgalactic gas? And the answer is yes. Yes, we do. Funny enough, actually, we have the first evidence of this back in 1959 by Lyman Spitzer, the same Spitzer of the Spitzer Space Infrared Telescope. What I'm showing here is probably one of the cleanest and clearest examples of some of these clouds that I'm talking, or some of this mass that I'm talking about. So the first thing is that we have this object here, and we have our background object. So again, this hot object that's emitting a spectrum. In this case, it is a very bright galaxy, which is called an active galactic nucleus. We can see is we can basically use the same physics as the Doppler shift, where you have the experience of having an ambulance come towards you, and the pitch goes up, and then if it moves away from you, the pitch goes down. So we can do the same thing with light. What we can see is that at the very front of this, what we call high velocity cloud, you end up seeing a pretty high velocity. And once again, this is something like 90 kilometers per second. So that's, upwards of 220,000 miles per hour. It's an insanely fast cloud. And then thankfully for this particular object, we actually have multiple sight lines that we can see through. And you can actually see that this follows the trajectory that one would expect for a cloud that's actually falling into the Milky Way, which is kind of interesting. So we can see here, as if we were to just project where that gas cloud is going to be and where it was before. We actually don't truly know the origin of this cloud. It's very likely, though, that it was ejected from a supernova in the Milky Way. 70 million years ago, didn't look like it was too much. Now we're observing it, and it's very likely going to fall in onto the Milky Way in about 70 million years or so. So that's interesting. This is only one example, though, right? So, like, are there other high velocity clouds that exist in the Milky Way? And it turns out that the answer is yes. There is a whole bunch of them. And so what I want to do from now, or from here, is to try and appeal to the naysay astronomer, right? Evan, so you're telling me that there exists this diffuse circumgalactic gas that I have not seen, even though I've been to darkest skies in the world. How does that make any sense? And frankly, to the naysayer, that is a very fair question. So the answer to that is related to the second point that I showed earlier, and using Kirchhoff's laws for spectroscopy, that this gas is very diffuse. So question then is, well, how diffuse is it? So we're going to take a look at something that we're pretty familiar with, which is rocks, right? And we're going to actually convert this to units that are useful for astronomers. So a granite rock, which is the rock that basically comprises the majority of the San Gabriel Mountains. If you were to convert this into the units that we actually use as astronomers, it's something like 2 times 10 to the 22 atoms per cubic centimeter. For those that are curious, it's around 2.5 grams per cubic centimeter. And then just for those that aren't really grasping this is a 1 or really a 2 with 22 zeros after, right? It's a lot of atoms. And of course, right, a cubic centimeter is something like this big, right? Okay, cool. Well, that's a very dense object, right? But what about the air? The air is actually also pretty dense. There's about 5 times 10 to the 19 atoms per cubic centimeter. So still 1,000 times less dense than a rock. So if we were to go and look at these same numbers and compare them to the densest, or one of the densest places in the universe, or sorry, in the interstellar medium, like this here, this is one of those dark clouds that I talked earlier. This is actually a pretty dense object, and it's sitting at more than 100 atoms per cubic centimeter, which is pretty wild, right? Like that's very, very, very small compared to the stuff that we deal with on a day-to-day basis. What about the circumgalactic medium? Oh yeah, it's bad. 10 to the minus 6 through maybe 0.1, so less than 1 atom per cubic centimeter. And as a reminder, for 10 to the minus 6, that is a 1 with 6 zeros in front of it. So there's no way that we're seeing it in emission, unfortunately. With a little asterisk there, we actually can't. But for the purposes of where we're at right now, that's what we got. So I think another natural question that comes from this is like, well, the CGM is very diffuse, so like, does it actually matter then? And I think I had to show this to sort of give you now the full story of galaxy evolution here and the different parts of the galactic ecosystem. So as I said earlier, we have the interstellar medium. This is where we reside and where you have all the dynamics of star formation, as well as feedback both from stars as well as from supermassive black holes. And as I showed earlier, we have outflows that get driven by stars. And those outflows have sort of one place that they can go, the circumgalactic medium. Once this mass makes its way out to the CGM, that's the answer to the question, by the way. This is where it goes. It either has the option to sort of mix around and fall back onto the galaxy, which will then fuel future star formation with these old metals, or it'll make its way out to the intergalactic medium, which is the mass in between galaxies. While that's happening, gas is actually falling in from the intergalactic medium through the circumgalactic medium back onto the galaxy itself. So what I'm saying here is a CGM, therefore, then, is a massive reservoir of gas that's been ejected from star formation as well as other feedback processes, recycled gas that's basically a mixture of this pristine gas coming from the intergalactic medium, as well as the ISM, as well as this new gas that may end up going in completely untouched, which is not likely, but possible. And we've sort of known this for a little bit. So over the past maybe 15 years or so, this has been a big hot topic, trying to understand and get better constraints on what the circumgalactic medium actually looks like. And it turns out that the CGM appears to be sort of similar to the atmosphere of the Earth. So in other words, another way of thinking about the circumgalactic medium is the atmosphere of a galaxy. So just like in the atmosphere, or sorry, just like on the Earth, if you want to try and understand how what water is actually doing over time, you have to account for the atmosphere in that process. It's called the water cycle, right? So you have the water itself, but in this case, we could say it's in the ocean, runoff from a river. I think it's heated up by the sun, and there's a phase transition going from water to water vapor. Then that water vapor then condenses into clouds, which then become dense enough that they start to precipitate that water back out, and then it gets collected, and there's this whole cycle. This is very important for life on Earth. And again, if you want to follow water, you need to understand the water cycle and account for the atmosphere of the Earth. In a very similar vein, if you want to understand how mass moves over time for a galaxy, you have to account for the circumgalactic medium. And this is very important for star formation, right? So in our case, with the atmosphere of the Earth, it's good for life, and for galaxies, it's very important for future star formation. And this is what we call the baryon cycle. In other words, the visible matter cycle. And so this is basically similar to what I showed earlier before, where you have gas that ends up falling through onto the galaxy itself. You then have star formation that then injects this gas upwards. And then you can have some intermediate regimes where some of the gas actually falls back onto the galaxy itself. Now, this is a pretty wild picture, right? In the sense that, like, how do we know this is actually happening? There's a lot of dynamics that's going on here. So I think a good question that we can always ask ourselves is sort of an appeal to intuition. Do we actually even see this in the Milky Way? And the answer is yes, we do. Yes, we do. We're actually going to go back to looking at these high velocity clouds that I was talking about. And we're going to break these clouds down into really three parts. So the first is everything that I'm showing here in blue are clouds that have velocities here that would imply that that show explicitly that the gas is coming towards us. In other words, it's coming onto the actual disk of the galaxy. In other words, we do have direct evidence that there is gas that's infalling from the intergalactic medium and the circumgalactic medium, some combination of the two, onto the disk. Well, what about this outflowing gas that I was talking about, right? Well, we already had pretty strong evidence to show that this does happen, but what about for the Milky Way, right? Because it's good to see. Sure enough, we do. And again, and the way that we can see this is this Doppler shift of, again, gas moving away from us. Well, what about this recycling that I keep talking about, right? Like we have gas that gets emitted, that gets ejected, then falls back onto the interstellar medium. And yes, this is exactly what we have. This is actually a really hard measurement to figure out. It's like, what is the gas actually doing, what the origin is, because with the high velocity clouds, you know very clearly because of how large the velocity is that it's either out or it's on its way in. It's really hard to get that in between. But if you look at, for example, the metal components and the metal composition of some of these clouds, you can see pretty clearly that, or not clearly, but it's reasonable to assume that yes, this is actually gas that's recycled. So what I want to do with these last few slides is sort of give you the, like, why do we care? Why does all this matter, right? Well, it turns out that we have a lot of theoretical expectations for how much hot gas should exist outside of the galaxy itself. This is literally just if you were just to write the equations by hand, if you just have a gravitating system, there should be some characteristic temperature that this gas should be at. And so what folks have done over the past 10, 15 years or so, they've tried to account for all of this gas that I alluded to earlier. Where is all of this stuff? And it's a little bit model dependent, which is why these numbers can vary so significantly. But depending on your favorite model and how you do it, yes, just about all of the baryons just about all of the visible mass that we think exists out there is indeed, just about all the mass that we know is missing does appear to be out in this circumgalactic medium. So that's one of the really interesting things too. And I just want to sort of pause for a moment and just remind that without including the circumgalactic medium, we literally can't even get the mass of the galaxy correct, right? So it's very, very important. We need to include this in our future understanding. And I sort of mentioned this earlier, but galaxies they end up running out of gas over time. And in the case of the Milky Way, we have lots of evidence to show that it's been forming stars for a very, very long time, but that it should have ran out of gas at some point. So where does that come from? And I just showed in the previous slide that we have this infalling material that will indeed fuel the next bouts of star formation, which is pretty phenomenal. So on these last couple of slides here, I want to talk a little bit about my research. It's really just going to be posed questions. So if you have more, please ask me during the Q&A. So some of the questions that we still have about the circumgalactic medium is, how does it actually change over time? How exactly does this mass actually fall onto the galaxy? Is it accreted along the actual disk, or does it fall down as a fountain? How do distant galaxies and their CGM, how does that actually change compared to what we're seeing in local galaxies? If you notice, everything that I talked about here is everything these are all very nearby galaxies, and stuff that I'm looking at are very distant. So what is the difference, and does that actually matter long term? And as I mentioned before, there are different phases, right? Like that you have a cold CGM, hot CGM, a warm CGM. Where does that actually come from? And finally, this is more of my question. I'm not sure if the community actually, ponders this, but I do, which is that are there any other effects that the CGM may have on galaxy evolution that we just don't even know of yet? And so what I'm showing here is some of the galaxies that are a galaxy that I spent a lot of time studying over this past few years that shows exactly the situation that I was talking about earlier, where you have a faint galaxy with some bright object that allows you to see the CGM of the galaxy. And these are really, really, really hard to find. And I alluded to this earlier, but when I said that you can't actually see the CGM emission, depending on the element that you're trying to look for and really the wavelength, you actually can. So in this case, we're seeing hydrogen that's being emitted from a very, very bright galaxy. So I know we're getting to the end here, so I want to give us all a movie. Thank you for your time here. I'm showing a simulation of a Milky Way mass galaxy, actually made by folks who were at Caltech. They're part of the FIRE collaboration, including Dr. Cameron Hummels. What we're seeing here is the formation of a Milky Way-like galaxy starting from basically time equals 0 to nowadays. The colors here show, the red here shows diffuse or hot gas, and then the white shows cold and or dense gas. And if you notice, I'll restart this once more. We now see that this is the center, like the disk of the galaxy, but in the very early part of the simulation, you had no idea what was going on, right? You had a bunch of mass that was being ejected that ended up falling back at some point, and while that mass was actually out there, it looked like it was interacting with itself. And so I'll go back here. That's once again, we have the colors change. We had these variable shocks that end up driving up the temperature. We can see now all of these explosions. So we're getting close to what's called cosmic high noon, where just about every galaxy was driving galactic outflows. And this is incredible. So you can, if you're just to trace one little parcel of gas, you can see that some of it just gets completely ejected from the system and some of it ends up falling back over time. And so the point to make here is that galaxy evolution is a complicated, messy process that involves the ISM CGM and the intergalactic medium exchanging mass over time. And you also have mass changes. And what we're trying to do from the observational perspective is basically take snapshots of this entire process going from redshift or from very, very distant galaxies all the way to now. It is an insane endeavor and it's really, really difficult, but that's why we do this, because it's fun. Right? So I'm gonna go ahead and give my conclusions here. Hopefully I've convinced you that we want to truly understand how galaxies evolve over time. We have to both look inside and out. And as a reminder, inside is the interstellar medium where you have star formation. This is where we live in our own galaxy. Outside is the circumgalactic medium, or this diffuse reservoir of gas that doesn't seem like it's important, but it's very, very important, especially for the long-term prospects of the galaxy. Without accounting for the CGM, you can't get the total mass correct. Excuse me. Ejected mass that you end up, that should somehow be left in the halo just gets completely lost. The future star formation of that galaxy doesn't make sense. And so this all must be accounted for now that we're past the taxonomy or phenomenological understanding of galaxy evolution. And of course, I want to give a few acknowledgments here to all the fans. So my mom, grandma, my little bro, my late grandfather, rest in peace, my chosen family, my fiance, who's at home at the moment. Of course, the group that I've been working with, Chuck Seidel, as well as Evan Kirby. And as Cameron mentioned, if he wants to continue seeing some of the amazing work that I think it's all amazing stuff. I'll be at UCLA for a year, and then I'll be at Carnegie Observatory, it's right up the road actually, and then Princeton after that. So should be a fun ride, and I would love to take any questions that you all have. Thank you for your time.
Hey, we can take some questions from the audience if anybody has.
Yeah, thank you for the great talk, Evan. It was very illuminating. Can you more explicitly describe the interplay and such the difference between this like missing mass and the extent to which this like when we were first thinking about dark matter, then was this before the circumgalactic medium discussion? And we do know that that most of it does still seem to be this mysterious form of matter, but to what extent did this circumgalactic medium move the needle towards hitting that mark of the missing matter? I don't know. Yeah, if you could talk about that distinction and that trajectory, that would be great.
Yeah, absolutely. Thank you for the question, Sarah. So yeah, just to re-describe the question, which came first, dark matter in terms of missing mass or the striking black medium. So if I remember correctly, the dates are that it was in the 70s that Vera Rubin actually started to look at galaxy rotation curves. And the idea here is that you would expect the rotation of the galaxy to sort of plummet as you move further out in radius. And actually, there's a very simple equation that one could use to infer how much mass must be out there. And so what she was able to find, again, empirically, right, from the observations, which I'm always a huge fan of, that there actually exists a significant amount of mass out in the outskirts of these galaxies that you just would not expect, right? Naively, one would expect the rotation to follow what we see in our own solar system, where again you would see this sort of plummet as you move further out in distance. So that was back in the 70s, and that was actually again a problem. Like, you know, I would argue that's the beginning of us truly taking dark matter seriously. The timeline gets kind of interesting because, as I mentioned before, you know, the galactic, it was originally called the galactic corona, was semi-discovered by Spitzer in the 1959 or so, in the late 60s, or in the mid to late 60s. I'm not too sure if at that time they thought that there was missing mass, though I highly doubt it. I really do think it was these most recent surveys in the 2000s, again, that looked at, you know, tens of thousands of galaxies where we can finally infer, okay, yes, this actually is a systemic problem that isn't just, you know, singular one-off galaxy. So that's my understanding. Dark matter first, and then CGM. But yeah. Good question.
Other questions? Over there.
Hey, and thank you for your presentation. I was wondering what proportion of the missing matter is thought of being dark matter versus CGM?
Yeah,
currently?
it's a good question. So in this case, we're sort of taking the dark matter halo as like for granted. So the idea, I'll actually go back to the original plot here. Let's see. So the idea here is that, whoops, there you go. The idea here is that you have already taken account for how much dark matter mass that actually exists. I mean, really, what you're really counting for is the total mass of the galaxy. And so that's what we're showing on the x-axis. This measurement was actually made exactly the way that I just described to Sarah, where you look at the rotation curves of all the galaxies. Which is why this sample is so good, because only with these, you can't do this for every galaxy, basically. So what you do from there is you take, okay, cool, I have this total amount of mass. Based on what we know from cosmology, and again, from these space missions that give us these very fine parameters, how much of that mass should be invisible matter? And so that's what this black line here is. So and then as we can see, again, the color points don't actually match what that's supposed to be. So it's semi-confusing, but just to, I guess, try and answer it even more explicitly, this is already assuming that we have all the dark matter that we need, basically. And now it's asking the question, do we have all the visible matter that we need, assuming that we have, or, you know, given the fact that we already have all the dark matter accounted for. Is that okay? Okay.
Line up. Sorry, why does it line up the higher you go up the graph? Why is it only in the bottom of the graph that we have this issue?
Yeah, that's a good question. So funny enough, actually, it doesn't quite line up. There's actually a little bit of a gap here. So it turns out that as you go up a little bit more higher up in stellar mass, and there are actually a few different ways that you can show this, but there's basically no mass where you see all of the stellar mass that should be there. For the lower mass systems, what I mentioned before about this star formation feedback, the stellar feedback, that basically is ejecting a bunch of mass. But once you get to higher mass galaxies, you actually have other feedback processes, which would be outflows and jets coming from supermassive black holes. And so that's then the dominant feedback process. So short answer is none of it actually fits well compared to, nothing is where it should be. I think it's a good question asked, like, why does it get a little bit closer when you get to higher masses? My understanding is that it's because you just have a larger gravitational potential, and you can basically hold on to all that mass a little bit better compared to the lower mass galaxies here, where, you know, a single supernova explosion, you could basically disrupt the entire galaxy for the really small dwarfs, whereas that's not at all gonna happen for the more massive galaxies. Good question.
Additional questions? Snake.
Great presentation. Just been reading about some findings on from the James Webb Space Telescope on high redshift galaxies that the data doesn't quite fit with galaxy formation. Do you think your research is going to help change the models of galaxy formation, maybe better fit the James Webb Space Telescope data?
Yeah, good question. So for those that are unfamiliar, we seem to keep finding too many massive galaxies at during the very early universe. And so in that case, you can basically only rely on the interstellar medium to even see this stuff. It's actually remarkable that we could even see galaxies this far back for a few reasons. First is that there's a lot of neutral gas or a lot of atomic hydrogen that exists, so it's hard to even just detect, especially some of the most important lines that we need to identify the redshift of the galaxy. So in my case, even accounting for the circumgalactic medium, you would still have an issue. As a matter of fact, it would make it even worse because you would technically have even more mass, right? That's not being accounted for. That would make the models even more upset, basically. My understanding too, though, is that, and this is also my caveat to the audience, is that it's a pretty uncertain science to convert light to mass. As I've sort of made it seem like we could take it for granted here, and for nearby galaxies, it's not too big of an issue. But you become very, very beholden to your assumptions when it comes to the masses that you end up predicting over time. So, for example, one really important parameter or variable that's included in all these models to determine the stellar masses is how many stars have been formed for that galaxy over time, called the star formation history. And you sort of can pick whatever one you want to. So, and to give credit to the folks who are writing these papers, they basically show all of the star formation histories. But even then, you also have uncertainties within the stellar populations, like, what is the fraction of very massive stars that are being formed versus low mass stars? Like, it's a very, very uncertain science. But again, this is why we do it, because it's, that's what it's all about. So, a short answer to your question, just to be more explicit, it wouldn't help out too much. It would probably make it a little bit worse. But ideally, like my end goal, honestly, would be to try and actually do the studies that I'm doing now at what we would call intermediate redshift. So, this is around where the universe is about 2 to 3 billion years old. I would love to try and do this as far back as we possibly can, because again, I have this hunch that yes, the CGM is important at basically every part of the process. So yeah, hopefully that was okay.
Let's thank our speaker. So now we're going to, I'll release you. So essentially what happens now for the next hour or so, we'll have the telescope set up outside. They're all set up to look at various different objects in the sky. And in about 5 minutes, we'll get started in here with our Q&A panel, where we'll field whatever questions didn't get asked during that brief Q&A, as well as any other questions that you have either related to the content of the topic of the talk, or on whatever astronomy or physics or science you want to ask. Maybe not all of science. We'll do our best. But we'll have 4 of us up here to field your questions for the next hour. So we'll get started with that in the next 5 minutes. Thank you guys for coming. Thank you all for sticking around for our Q&A panel. So what we'll do is each of us will go through and just give a brief introduction to who we are. We've also got our names. Hopefully you can read it. I tried to use as thick a marker as I could find. Our names and kind of our specialties in terms of the specific scientific research that we do here. We are happy to field questions on whatever you may have, but these are the things that we most focus on. So we'll most be able to answer questions related to these. As mentioned before, I'm Cameron Hummels. I'm a research scientist and director of astrophysics outreach here. And my research is mostly on doing computer simulations like the final one that you saw at the end of Evan's presentation for the evolution of galaxies and the constituents of galaxy stars and clusters of stars and these sorts of things in the broader context of their environments, of the circumgalactic medium, that kind of atmosphere that surrounds galaxies, as well as neighboring galaxies, as well as kind of the whole structure of cosmology, the whole structure of the universe and how it changes over time. So I try and make predictions based on the simulations to compare against observations like those that Evan or Nick did.
Hi, I'm Kaustav. I'm a fifth-year PhD student here. So I work mainly on the observations of the explosive end of stars, which are called supernova. So Evan mentioned in his talk that when stars die, they basically give away all the material that they produced at the belly of the stars back to the galaxy. So those are important in terms of the context of today's talk. Also, just as a fun fact, so roughly we expect that every 100 years, one massive star explodes per galaxy, but there are billions of galaxies out there. So we expect that every second, as I'm speaking, there's one star which is exploding out there in the universe.
Hi all, I'm Nick Brzezinski. I work in the same group as Evan actually, so I'm studying the circumgalactic medium as well. And Evan mentioned that it's very difficult to study the circumgalactic medium in a mission. So it's been done in absorption, and we talked a little bit about absorption. So it's difficult to do. So my project is to see if it can be done in a mission as well. And how does the observations in a mission compare to the ones in absorption?
Okay, I'll introduce myself again. Yeah, okay, yeah. All right. Good to see you all. Good to see you all again.
We're happy to take questions from all of you if you have any burning questions that we might be able to address. Yes, you have a question we didn't get to during previews.
Thank you. Has there been any collaboration with, say, Jessie Christensen to look, she's also from Caltech, to see if there's a correlation between the different clusters and the amount of exoplanets found in the different regions?
So Jessie Christensen, as mentioned, is a scientist here who does a lot of work with exoplanets, planets around other stars. So the question is primarily, have we looked at correlations between the planets in these clusters and the abundances of those planets around the stars present in clusters versus in just stars that aren't in clusters? Okay. Right. I don't know the answer to that question. Do you guys know the answer? Sorry, go ahead, Nick, please.
Scale, I don't think we've looked at it extensively. I think that it's a little bit, from an observational perspective, a lot of the galaxies we look are in the earlier universe where we don't have the resolution yet to get down to the planetary scale or the solar system scale. But I don't know about it closer to home.
Well, so one of the things is observing planets around other stars is really hard. It's a hard problem. And that's why the first planet that we discovered around another star didn't happen until the last 30 or so years. And since that time, we've observed roughly 5,000 planets around other stars other than our sun. And that number is growing over time. But because it's such a difficult problem, we're only able, at least with the technology that we have currently, only able to do it for star systems that are reasonably close to us. I mean, not like they're still light years away. They're a long ways away, but close in the astronomical scale of things. Certainly not other galaxies. Those are far too far away. their stars are far too far away for us to be able to perceive if there are planets in them. But that is a good question, and I don't know the answer. There are only a handful of clusters that are close enough to clusters of stars that are close enough to us that we would be able to have the sensitivity to discover if there were planets around those stars. The Hyades, I'm thinking maybe the Pleiades.
I was also wondering, like, if you're wondering, if you talk about clusters, like globular clusters are usually a different population, like they're older, if I'm not mistaken.
They tend to be
They
older.
tend to be
Yeah,
older.
stars and tend to.
So if you could observe them, you might expect a population difference in the exoplanets you observe in those older globular clusters than you might with a normal field star, but that's more speculation.
It's a very good question, and I'm afraid that I don't. You stumped us. But we also don't have somebody who's an exoplanet specialist on the panel. So it may be something that's known, but we ourselves don't. But it's a good question. Additional, yeah, there's a question. Maybe we'll have better luck with this one.
I doubt it. So you mentioned that there's a lot of speculation and a lot of assumptions that happen in this type of research. How much of your research and how much of, I guess, any research that pertains to galaxies, how much of that is assumptions and how much of that is actual concrete evidence that we know is true?
All right, so I guess I will use this time to specify what I mean by assumptions. So the work that I do is all based on observations, and so from that respect, it's all like those are the facts, right? Like you have your data. There's nothing else to say about it, right? You have your data. What goes into the final product of the data that you end up analyzing, though, like that, there's lots of steps for that process. So, for example, the telescope data that we all look at, you have to take it from what you're seeing from the raw image that you're getting from the telescope to something that's science usable, that you can actually use for science in terms of like, extracting physical measurements and properties from it. That process has been pinned down to a science, although we still have a lot of work. As a matter of fact, Nick's project basically, he's trying to improve that exact process that I was talking about, going from, raw data to actually something science ready. So what I was saying about assumptions that go into, our findings, what you have, for example, is the spectrum of a star. So if you remember, or like the spectrum of a galaxy. So if you remember, that's basically where you just look at the brightness of the galaxy as a function of the color of that galaxy. What you see is what you get, right? Like that is not going to change. So what we need to do, and the reason that we even have jobs, is because we're trying to explain how those spectral features arise, right? And so depending on, for example, the color of that galaxy, how bright emission line 1 is compared to emission line 2, you can back out some things or some information about that spectrum, about that galaxy, that don't really require models that are robust. So like in my case, for example, I try to stick to as few models as possible so that you can, what you see is what you get. You can, immediately pull out physical properties. The reality, though, is that a lot of the data that I get is currently sort of uninterpretable in the sense that you have a hodgepodge of different processes that could be occurring at the same time. And so that's where you have to use and infer and make good scientific judgment as to what things you're going to assume about this particular object. So for example, the galaxies that I look at this is around the time that the universe was about 2 to 3 billion years old. We have found that if you were to look at a large population of these galaxies, you can actually assume that they've been constantly forming stars for their entire life, basically. And we have lots of evidence to show that that's a reasonable thing to do. Now, you can always find deviations from that. And so what we have to do then, of course, is to actually check every single galaxy against what we found to be generally true, and then correct ourselves as we see fit. So what I was saying earlier about the assumptions that are made into these models, like that's really what it is that you have your data. Like that you get, what you see is what you get. But the scientific judgments that you have to make, and what the physical properties are extracting from, that's where things can get hairy, and that's where you can have lots of differences, and sometimes even fights between different groups, like, oh, this is not right, that's not right, or so on and so forth. So hopefully that makes a little bit more sense. We're not just here assuming and being like, oh, that's that spectrum feels like it's a galaxy. Right? It's a lot more nuanced than that. So.
I agree with everything you said. The one thing I'll add to it is simply that, you know, when you yourself go about your day and you open your eyes, your mind is interpreting raw data from your eyes and the light that's striking your eyes, and it's interpreting raw data from your ears and the sounds, the impulses that are coming from your eardrum and so on and so forth. And your brain puts that together and interprets, like, right now you hear my voice and you see me moving, so you interpret that I am the person who's responsible for motion and the sound that you're hearing. But ultimately, at a base level, that is an assumption. That is an interpretation from the raw data that you are receiving at this moment. And our lives are a series of building on small assumptions that make sense. And we constantly check. Like, if all of a sudden my voice continues, but I'm not moving my mouth, you'd be like, what the heck is going on? Right? You can confirm that your assumptions are valid. And some of the things that Evan talked about, or some of the things that we talk about in these presentations or scientific papers, might seem like there are a lot of assumptions. But for something to be considered a publishable work in a professional journal, scientific journal, it really needs to pass muster with other scientists who are trying to act as the biggest devil's advocate. Like, you discussed this and you interpreted it this way, but what it could be that way. Are you sure that that's correct? To make sure that what actually gets printed and published is verifiable and is reasonable. And there are various different levels of kind of veracity that you have to meet in order for something to be a published work. So even though we say, like, assume, don't think it's just a bunch of people BSing or whatever. There are a lot of steps that go through this and other people who are checking. And at least in my own work, and I think many other scientists are this way, I like to be my own biggest critic. If, like, I'd rather be critical of the work that I'm doing instead of somebody else coming along and being like, this looks like a bunch of BS. What about this interpretation? So I think a lot of scientists really have this motive to make sure that what they're saying is valid and makes sense within the context of the observations that. Any other? Please.
I might just add to that. I mean, the sort of dovetailing on that. I mean, the fun part is too that there can be multiple explanations for the same event. And, you know, maybe if you go to the grocery store or something and you hear voices and this and that, that's not a good thing. But I think the fun of the science that we do too is that, you know, it's like, okay, this is a possible explanation. This is a possible explanation. And that can open up new avenues for research as well, as say, okay, maybe we don't understand this particular area well enough, and this research or this project or this galaxy, whatever, might lead us down a different direction and give us some new information that may help resolve that discrepancy eventually.
Additional questions? And then I'll get to some of the questions we've had asked from our YouTube audience as well.
So my question is actually about the equipment. So I wanted to know, you know, we had Hubble that served faithfully for a long time, and now James Webb. Yeah, still working. Is there any holes in equipment or technology that you guys are missing that would help, you know, observe the things you need to observe?
I mean, we'd like to look at all wavelengths at all parts of the sky all the time. It's not fiscally possible, but talk about some of, go ahead, guys.
Yeah, no, first off, the answer is absolutely. Yes, if we could have the largest telescopes with the best instruments, we would be so happy. And as Cameron was alluding to, you know, it's a pretty, you know, never-ending question. So I'll try and be more specific about what would be very helpful for my work. So the instrument that I'm using that's really has been, you know, pushing my survey forward is what's called a integral field unit, an IFU, or an integral field spectrograph. The idea is that you have a picture that you're taking, but every single pixel in that picture, you have a spectrum, right? So what you're effectively doing is combining at least two different observing runs into one. It's an incredibly efficient way to find galaxies that I care about. Now, we have one of those on the Keck telescope, the twin 10-meter Keck telescopes in Hawaii. Beautiful place, by the way. And what I would like is to have an instrument that's similar to that, but looking at a different wavelength. So right now we have this instrument looking in the optical, so the same wavelengths that you and I are looking at each other with. So I would like to have a integral field unit that's about the same size. And by size, I mean the field of view, about the same spectral resolution. So, you know, how finely you can break up the spectrum, but in the near infrared. And the reason is because I want to be able to see emission lines that we would be able to see with our naked eye, but at the galaxy, but for the galaxies that I care about, where they would actually get shifted into the infrared, the near infrared. So that's like one thing that I would really like to have.
James Webb can do. There are IFUs on James Webb, and it's in the near infrared.
Yes, that is true. I would like it in a way that I could actually get time though
Oh,
for
yeah,
that
that's
for
right.
that telescope.
It's so for these NASA space telescopes or some ground-based telescopes, they're very expensive to run, and not everyone gets to access them that might want to. So we refer to them being oversubscribed. So maybe there's like 10 times as many people who are trying to use it as there's available time on that telescope. I think James Webb is about 20 to 1. So there's like 20 times as many proposals as there is time, like actual time to use the telescope. And committees are formed to evaluate and read the different proposals of what Evan might want to do or what Kostov might want to do with the telescope. And then they say, well, we can only, you know, give 5% of these. This one does some really cool science and doesn't ask for very much time, so we'll give it. But this one asks for a ton of time, and so it's not worth the reward, even though it might be cool science. It's a challenge every year.
I just want to add on to that. It's not like, I mean, you talk about an oversubscription rate of 20 to 1. It's not like 90% of the proposals are bad either. This is a tough decision because there's a lot of very interesting science cases that come across your, it's like, oh, I'd love to do that. I'd love to do that. It's just, there's only so much time in the year, so to speak. Yeah. But sort of getting back to that point, I think you've got 4 astronomers here on this panel. You're going to get 4 different answers as to what they want. But we could go down the panel and ask that. But you're going to find that, yeah, it's always a competition between how many nights there are in the year. So you want, and sort of to Evan's point, so what kind of spectral resolution do you want? So as an observer, your bread and butter spectra tends to be images. Those are the data that you can get, the raw data that you can get. So from an imaging perspective, you want the highest resolution camera that you can get, so you can really resolve the faintest details and look right next to something and say, oh yeah, those are 2 different things. And from a spectral point of view, you want something that has a really high spectral resolution, so you can say things are moving at 10 kilometers per second versus 11 kilometers per second. Instead of 10 kilometers per second and 100 kilometers per second. So that's another thing. Unfortunately, there's no free lunch, and physics and fiscal requirements require that you make some compromises. But yeah, depending on your science case, you may want 1 or 2.
Great. Yeah, the answer for me is we need more UV and X-ray telescopes. Because we can't see those from here on Earth with a visible wavelengths of telescopes. We can see it because our atmosphere is transparent to that, but the ultraviolet and the X-ray, our atmosphere is very effective at blocking that, and so you have to get above the atmosphere.
Thank goodness.
Yeah, thank goodness. It would be bad for us if those photons came parading down and messed up our DNA and such. So that's good. But in order to see those sorts of phenomena, we have to get above that atmosphere to be able to perceive it. And right now, the only UV telescope in that's operational is Hubble. And as you mentioned, Hubble is not long for this Earth. It will probably run out of its various parts in the next few years. It's been operating basically nonstop 24/7 since 1990. And it's very old. And the Chandra X-ray telescope, another NASA space telescope, has been operating since also in the 1990s. And it's getting long in the tooth as well. And it's expected to kind of end its mission in the next few years as well. So we'd like to get some more about that. You have a follow-up question. Is there work being done to use decommissioned satellites to bring them back up? It turns out that there is a new mission called the Nancy Grace Roman Space Telescope, the Roman telescope that it's referred to. This will be an infrared space telescope. And if you look at it, it looks a little bit similar, a little bit familiar. And that's because it's the exact same telescope in terms of the body of the telescope as the Hubble Space Telescope. It was a leftover telescope from the SPY, basically the SPY satellites. Obviously, the SPY satellites are doing a different task. They're looking down at the Earth as opposed to up from, towards the rest of the cosmos. But they just had an extra one lying around because the Department of Defense has a lot more money than the National Science Foundation. And they were like, we're not going to use this. You guys can have this. And so a lot of work has gone on over the last 10 years to commission cameras and such that would be appropriate for making this an astronomical telescope. And it's meant to launch in the next 2 years. So that's one example, but oftentimes it isn't quite so tit for tat where you can just grab an old decommissioned one and then send it up. It will be in orbit. It is not yet. So it had never launched. I don't think it was actually ever used. I think they just had a surplus and were like, we've got the next version of this down the line. We don't need that old fuddy-duddy. Do you guys need this? And we're like, yes, that would be wonderful. The Hubble Space Telescope has probably been the most productive scientific instrument in the history of humanity. If you want to give us an extra one that we can fit with some additional cameras and do additional science with, that would be wonderful. So they gave it to us astronomers, and astronomers have been outfitting it to go and do some amazing science in the next few years. There's what? Oh, there's probably many in orbit that are looking down at us and doing whatever they do with that data. But I don't think that the DoD and National Reconnaissance Office are like, they're like, turn it up and look up at the sky. Because I'm sure they care, but. Well, so there's oftentimes the cameras that are on these things are meant for doing high resolution observations of things on the surface of the Earth, which are different than the sorts of astrophysical cameras that we might have. In the same way that if you take your iPhone and you take a picture, it might be perfect for taking portraits of a friend, but it may not be as good for taking astronomical images or spectroscopy, where you break it into the various different colors of light that are coming from distant objects. So it's not just like grab this and stick it in space and make it work for whatever we need. It does take a number of years to build the instruments that make it work for what we need it to do. We don't get to look at the SPY satellite stuff. That's why they're SPY satellites. So we can't look at what they have, or, they're welcome to offer us things, but that's all behind the fence. And that is what, I know oftentimes the government feels like a single structure, but it does have many different components, and the NASA people and the National Science Foundation people are not privy to what's coming out of the Department of Defense and the SPY stuff. So if they want to give us stuff, that's great, but we don't get to let us look at your inventory of things. We'll pick out what we want. No, they're not going to do. Go ahead.
But I might add to that. I would say that astronomers, especially that are building instruments around here, are quite resourceful. And I think that a lot of times there's evidence like this integral field unit that Evan was talking about here, that they're looking to build another one of those. And to do that, I believe, I don't have the exact details on this, but they might be taking a gondola, or they might be taking a detector that happens to be in the closet up at JPL, and someone from some old project. And it's certainly the case that detectors for new instruments, it's sometimes a lot cheaper to just sort of go down the street and say, hey, this is surplus, or this hasn't been used before. And it's much cheaper than buying a new detector. I mean, you got to weigh that against the fact that the newer detectors are probably more efficient and you can maybe get more, but it is certainly a lot cheaper to go down the street to JPL or go to Keck and say, hey, we're decommissioning an instrument. Can we have that detector? Can we have this component? Because there's some things that are similar between all these instruments. So, but yeah, certainly that is done.
One quick announcement. There's about 20 minutes left on the telescopes. So if you haven't had an opportunity and you want to look through the telescopes in the next few minutes, I'd encourage you to head outside to take a peek. I wanted to ask one of the questions. There have been several questions from our YouTube audience. One user asks about AGN. So AGN, you mentioned it during your talk, are these active galactic nuclei. They're supermassive black holes in the centers of galaxies, and they do stuff there sometimes. And the question is, how can AGN affect the evolution of galaxies, but also the atmospheres, the CGM, the circumgalactic medium around those galaxies?
Yes, so that's a great question from the YouTube audience. And the answer is pretty significantly. The AGN can have a huge impact on the CGM, both in terms of the amount of gas that is out there, how brightly that gas shines, and then AGN also have another pretty strong effect on just the evolution of galaxies just in general. As a matter of fact, one of the more interesting things I didn't get to mention because, you know, it's a short talk, was that there appears to be a very strong correlation between the mass of a galaxy, or sorry, the mass of a galaxy supermassive black hole, and then the actual physical properties of that galaxy. So the reason that that's remarkable at all is because, you know, the mass of a supermassive black hole compared to the total mass of the galaxy, I mean, we're talking about, you know, orders of magnitude, right? Thousands, million. Yeah, actually, I'm sorry. Yeah, between, you know, 100,000 to 1,000,000 times smaller than the actual total galaxy itself. So the fact that there's any relation whatsoever is actually pretty insane to think about. And that's an open question. Why is that? So, as I mentioned before, there are a few different types of feedback where you can have these, you know, these galactic winds or these outflows that come from galaxies. One was again from stellar feedback, and the other can be from quasar feedback. And it turns out that even in our data set, we have examples of both of those. So galaxies that we're looking at, they ubiquitously have outflows from the star formation. And then the quasars that we have, or AGN, that's another type of quasar, also have show examples of outflows. You also see lots of emission in the circumgalactic medium of these galaxies too. Which is again one of the things that Nick is actually focusing on in his work. It's a little bit limiting because, you know, you can only look at certain elements. You like to look at the whole enchilada, as they say, but it's really difficult. So short answer is yes, the AGN can have a pretty profound impact on the entire ecosystem, and there's still lots of open questions around those effects.
I just to add to that, what's cool about the AGN is so they are their own systems, they are their own beast, exactly, and there's a whole bunch of fun science that can be done there. But if you take an AGN, or you take these quasars as an example of that, of one, these can be bright and they can be used as background sources to study the circumgalactic medium of galaxies in front of them in terms of distance. So if you understand a little bit about AGN, you understand a little bit about the spectrum, you can use them as a background source with which to study gas.
Yeah, just I think someone earlier asked about this observations from JWST that there were lots of very luminous galaxies very far away. I think one of the explanations that has been offered is that maybe all of the light is not actually coming from stars, but rather a big contribution for that light is coming from AGNs. So that might also be an explanation that you can sort of explain why you see this very luminous galaxies very far away.
One more question from our YouTube audience before I get back. There was a question related to dark matter, since you touched on it, and there were a couple of previous questions. And that was, is it possible that the dark matter that we think is out there based on some of the observations, the indirect observations of it, could it just be diffuse gas that we don't think should be there? Or does it have to be some more exotic type of stuff, like different matter?
Yeah, it's a good question. It would, yeah, I don't know why I'm confusing myself on this one, but yeah, it seems like it's very unlikely that it's actually CGM gas that actually is what dark matter particles are made out of. You can actually look at this a few different ways. The one that I'm trying to think of, right, or that I'm thinking of at the moment, is just the inferred mass that one would have to have if you were to translate the effect that dark matter has on the light that, again, that's in the galaxy, versus the expected mass that one would expect to see in the circular galactic medium. It's just not even close. The numbers that I can give for the Milky Way is that the dark matter halo of the Milky Way is something like 10 to the 12 solar masses. So it's a math. It's a 1 with 12 zeros after it times the mass of the sun. Whereas if you were to account for all of the visible matter that we could see, even if you don't necessarily include the circular galactic medium, you're still at 10 to the 10. So 10 with a 1 with 10 zeros after it. So we're just talking about two completely different mass ranges. But it's a good point. I like the connection that's trying to be made. But at least from the observational side, yeah, they're very different, unfortunately.
Yeah.
It'd be nice to explain dark matter, but
certainly the search for dark matter and not having to invoke some sort of crazy unseen component is, you want to look for all the people are like, what did you think about black holes? Could black holes be dark matter? What about rogue planets? What about all these other things? And believe you me, scientists have tried to think of everything that they can and still nothing fits the bill. Because as Evan says, some galaxies, something like 95 to 99% of their mass is the dark matter, compared to like 1 to 5% is the stuff, stars and gas and baryons, the stuff that we're made of. And so it's like, yeah, it doesn't all add up. There has to be something kind of exotic and wild. In addition, yeah, that's right.
There would probably be a luminosity. I mean, not all of the CGM is luminous and bright in emission, but if most of the mass that we attribute now to dark matter was part of the CGM, I mean, you'd probably see a decent fraction of it, and we don't, and we're pretty sure that we know where that missing light would come from.
So, additional questions from our in-person audience. You had your hand up, and you as well.
Thanks, guys. Evan, great presentation, and beg of luck in a few weeks. I'm wondering if you can clarify when you say the mass of a galaxy. My simple question is, what are you talking about? But specifically, I guess, do you mean everything, like the mass of all the objects within that galaxy, or the amount of space that galaxy takes up in space? Can you clarify that? And then the second part of my question is, from a practical standpoint, how do you measure and calculate that? Is it through looking at images from a telescope and being able to draw conclusions, or some other method that's above my head? I'd love to hear you talk about that.
Yeah, for sure. Great question. And somewhat of a nuanced answer for what it's worth. But I'll be as direct as possible. Really, when I say mass of galaxies, it's really just two masses. It's the total mass, which would include the dark matter halo, and as Cameron mentioned, it just dominates the total stellar mass. Again, I can use the example back of the Milky Way, right? It has 10 to the 12, so 1 with 12 zeros after it. So even if you don't include the other mass I talked about, which is the stellar mass, or the baryonic mass is what we would call it, that's only 10 to the 10. So even if you don't account for it, you're only changing the decimal place by 0.01. So it's very, 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 very different. And in our case, the reason that we always like to focus on, or at least I should say in our group like to focus on the stellar mass, is because we can actually observe that. It actually becomes really difficult to try and infer what the halo mass of a galaxy is, unless you can get either the galaxy rotation curve, like I mentioned before, where you can literally just plot out like what is the velocity of stars as you go further out from the center of the galaxy further, or you can use what we call lensing, gravitational lensing of that galaxy, and this is where you can actually see how the dark matter is affecting the light that's behind it, and use that to infer what the total mass, and in this case, it will be the dark matter mass of that galaxy would be. So that is the practical way that one would do it. It really is the ideal way. The practical way that we would do this, especially in our group, we're looking at more distant objects, is you're going to really rely on what's called the mass to light ratio. So within your stellar population model, which basically just models if you were to have a explosion, or sorry, a burst of star formation, and you have a bunch of those, what would be the properties of that galaxy? Baked within these models that we have is what we call the mass to light ratio, which literally says if you have this much light coming from this source, then it should translate roughly to this amount of mass. And those are typically calibrated with galaxies that are nearby, because you can actually get the multiple measurements, right? You can get the measurement from the mass, just from like some galaxies you can actually just count the stars, and then use the dynamics from those rotations to get that. And then from there, you can apply those to higher redshifts. That's also another source of uncertainty as you start to go higher and higher in the more distant galaxies. So just to summarize, I really mean two masses: the total mass, which is really just the dark matter mass, and the second is the stellar mass. And in this case, really, stellar mass just includes anything that that emits light. And in that case, that would include the gas and the dust and the stars, anything that we can actually interact with. That's the question.
What was the question? Like, how do we measure the total mass? Into mass.
Mhm.
Yeah. So as Evan said, for something like that, the image that you held up of just a Hubble Space Telescope image, you can count up the number of stars there or use some sort of calibration where we could count the number of stars. But for getting that dark matter, it's really based on dynamical effects. Because you see, right, and you talked about this during the presentation, you see galaxies spinning. Like the canonical view of what a galaxy looks like is that spiral galaxy with spiral arms. It's clearly rotating, right? And it's rotating at a certain speed. And we can measure the speed at which it's rotating by looking for spectral emission lines and stuff and seeing the Doppler effect. But if you have something that's spinning fast enough, it's just going to spin itself apart, right? It would just fling it in the same way. If I start rotating, moving around in a circle, as I move forward, my arms start to go out because of the centrifugal force that's pulling it out there. And the more and more I spin, eventually I'm going to reach, I mean, let's not do it here. I'm going to reach some sort of speed at which my arms fly off and I explode. It'd be bad, but it could happen, right? It works with your intuition. And it's the same thing with galaxies. And so if you look at these galaxies and you see how quickly they're rotating, how quickly they're spinning, you know that there has to be something that's holding them together, that's preventing them from flying apart. And the attractive force that holds galaxies together is gravity. And gravity is related to the amount of mass that's there. And if we count up the individual stars or count up the amount of light that's there, we know there's a certain amount of luminous matter that's there. But based on the fact that it's rotating at a certain speed, but not flying apart, means that there's some additional mass there. So you can figure it out based on the dynamics of the system. So that's one way in which you can measure the mass of a system simply by, instead of going there and counting individual stars or being able to count this unseen dark matter, it's by looking at the dynamics of the system.
Yeah, but you kind of noted at the beginning of your question, it comes off as kind of a simple or naive question. It's like, oh, what's the mass? But it's a nuanced question, and it's something that has a lot of uncertainty involved, and it's something that it's a challenge. It really is a challenge especially for a system that may be completely new. It's sometimes easier if it's like, oh, we know what this kind of thing is, we know how to measure it. But yeah, if you're looking at something completely new, it's definitely a challenge. It's like measuring a distance too. It's something that's a real easy question to ask. Oh, how far away is that? But actually getting a precise answer to that and something that you can trust is a much harder problem.
You had a question.
Yeah, thank you. Hearing the panelists elaborate is, even more informative and illuminating. So this is exciting. So I had two questions. First, you talked about how it's important to get a snapshot of the different stages of matter cycling through this, galactic matter version of the water cycle, right? So are you getting these different snapshots at different redshifts? Like, have you gotten to a point where maybe you've noticed, I don't know, a cyclical trend as a function of redshift? Or I guess what is the, I guess, independent variable through which you're seeing these different snapshots? And then I guess my other question is, Gustav, I noticed that supernova and stars are a little different, so I'd love to hear from everything else so I'd love to hear a bit more about where you come into play in all of this.
Without Gustav, we don't have a galaxy. It's as simple as that. So.
Yeah, so great question. And it is very, very, very difficult to do so. So the short answer is what you have to do is look at a large ensemble of galaxies at different distances. And so you use the right word, which is redshift. For those that are unfamiliar, this is basically how we till it gives you a proxy for the time in which the object was formed, and it also gives you a proxy for the distance to that object. So as I sort of, or as you implied, and as I mentioned during the talk, we really only get to see snapshots of the cosmic movie of any given galaxy. So what one has to do is, if you're trying to, for example, understand all of the galaxies of a particular mass at, let's say, redshift 2, the redshift that we care about, you have to try and look at a bunch of different galaxies of that same mass, of those same properties, and see how they differ at that redshift at that time. Then you want to take a look at how that same type of galaxy changes as you move to, further and further to where, or closer and closer to where we are. So in other words, the way that we fill in this cosmic movie is try to find as many similar galaxies as possible at different distances to try and connect all the pieces together. We also have other ways of doing this. So for example, in the galaxies that we look at, we know that mass is outflowing because we can see it pretty, like, very, very, very clearly in the spectrum of the galaxy that we have. So for example, we see that blue shift that I was talking about, right, where like matter looks like it's coming towards us. We can actually see that very, very clearly in different metal absorption ions that we see in the spectrum of these galaxies. We also know that gas has to be funneling in or has to be funneling onto the galaxy, because if you were just to do the exercise and say, well, this galaxy is forming stars at about this rate, how long would it be before it just runs out of gas completely? It's a very, very short time. And we know that galaxies form stars over their entire lifetime, for what it's worth, with some caveats there. So we know there has to be some flow of material of gas that's coming onto the galaxy itself. So this is all to say that there are multiple ways that one can infer this. And the ideal case is to, again, take these different snapshots. Well, really, ideally, you'd be able to track a galaxy from the beginning of the universe to now. But from a practical standpoint, that's what we have to do, is, again, try and find galaxies of similar properties at different distances to try and make this complete picture. And then even if we don't have very many galaxies, you can still use physics to infer that these processes must be happening, or if they're dominant compared to other processes, or subdominant, so on and so forth. Good question.
I think I just wanted to highlight a point that Evan made here, and I think that astronomy is a unique science in that our laboratory is the universe. And if you were talking to a biologist or you're talking to a chemist, you might go about and you ask them how they run their experiments. They would say, well, I'm going to make a bunch of flies, I'm going to grow a bunch of plants, and I'm going to vary different things about them. I'm going to adjust this gene here. I'm going to, try sodium instead of whatever element or something. And in this experiment, and they'll run a whole bunch of trials, and they'll do it all in the lab, and then they'll come up with their results at the end, and they'll be able to say pretty clearly, oh yeah, well, I've varied this parameter, and because I varied this parameter, something X, Y, Z happened. And I think that what's unique about astronomy is we don't have that ability. We can't fly out and tinker with these galaxies and say, oh yeah, let me just remove that star and see what happens. Would be nice, but we can't do that. So the next best thing we have as a proxy here is to say, let's look at a whole bunch of galaxies. And if we can sample the diversity of galaxies or stars or whatever we're looking at up there, then we can use that, the large sample, to be able to say, oh yeah, well, we expect them to behave in this certain range, and these galaxies apparently have these properties which appear to be correlated with certain effects. So it's a little bit of a different science experiment, but that's how we go about doing it. Anyway, I thought that was an interesting.
Hence, we are called observers and not experimentalists. So coming to the second question, so I can start by asking a thought question, which is, what sets the maximum mass of a galaxy? So Evan said that it's, for example, a typical galaxy like a Milky Way is 1 followed by 12 zeros. So why not 1 followed by 17 zeros? So right, what sets the upper limit of how much mass a galaxy can have? So to answer all of those questions is in part the feedback process that Evan mentioned in the slides, is that once you start forming a lot of stars, nature sort of always has a feedback mechanisms where it's like, oh, this is too much. So let's now throw back all that gas out into the outside of the galaxy, which sort of might be one of the main sources which actually forms the circumgalactic material. So I would say it's what forms the CGM. So supernova explosions play a major role in that. Exactly. Yes. Yes. I think I said that in one of this Q&A talks.
Like puking after you've drunk too much. That is, so our online audience gets that, because that is a good point. Yeah. Oh, there was an online question also pertaining to cost of, and that was, Do all stars turn into supernova?
The yep, the lucky ones or the unlucky ones. Well, lucky for us. Yeah, so it's a great question. So the way a star works, for example, right now we know that the sun is, for example, shining well and is quite balanced out. We know that, for example, at least the sun is not going to blow into a supernova explosion tomorrow. Is that, for example, a star is made out of a lot of mass, and what's holding it is, so there's gravity pulling it in, and there's radiation pressure from the center because hydrogen is burning into helium, and that's producing a lot of heat and radiation pressure. So currently the sun is in sort of a equilibrium. So you can think of it as like a tug of war where radiation pressure is trying to push it out, gravity is trying to pull it in, and that's currently in sort of a balance. But one day, all of the hydrogen that's there in the core of the star is going to be burnt out. So for example, just like a car runs based on how much gas it has, but it would stop once it runs out of the gas. Similarly, a star would stop burning fuel once it runs out of this hydrogen and so on. So depending on how massive the core of the sun is, or core of the star is, if the core of the star is massive enough that it basically keeps on producing heavier and heavier elements till it no longer can produce this outward force that is balancing out gravity, what would happen is that the entire core of the star would basically collapse. And this collapse is what gives off this so-called supernova explosion, which basically in a few seconds, for example, a star lifetime is a few hundreds of million years. In a few seconds of a supernova explosion, it gives out equal amount of energy as that of an entire star burning through its millions of years. So it depends on the mass of the star. So the rough number is if a star is, for example, more than around 8 times the mass of the sun, yes, it would undergo a core collapse supernova. If the mass of the star is less than around 8 solar mass, for example, like our sun, it won't undergo a supernova, but would rather expand. Maybe it could engulf, for example, the Earth, but don't worry, that's another 5 billion years away, and ultimately form something called a white dwarf at the center.
Great. That was a good explanation. Thank you, Gustav. Additional questions from the audience?
For stars that leave behind a supernova remnant, like a neutron star or something else, what is the state of the core just before it collapses? Is it degenerate matter similar to the neutron star, or is it different? And at the end of the explosion, you get the neutron star.
Yeah, so just before it, so the way the entire thing happens is that, for example, I was mentioning it's initially the radiation pressure that's balancing it. Once it runs out of that, then basically the core is it becomes a more dense, more higher temperature, higher pressure system. So as a result, you have more degenerate material that's formed. So that tries to then balance the gravity. So if, for example, in a white dwarf, it's something called this electron degeneracy pressure. So it's basically saying that no two people can occupy the same address. So it's sort of saying that two electrons cannot occupy the same quantum state. So as a result, it applies something called an electron degeneracy pressure. So for a white dwarf, that's what's balancing gravity. If the mass of the core is even higher, that's not enough. It collapses further into finally, basically the proton and the electron all combines to form neutrons. And it's this neutron degeneracy pressure which holds on against the gravity. So the core is entirely degenerate material, but the outer envelope of the star, basically it falls onto that degenerate core and then bounces off it. So the material that's ejected out right outside the core is just normal stellar material that's mostly just gas. It's caused by the infall of all the stellar material. So it's, imagine I have a ball and then I throw it very hard at the table. It's going to go down, but then it's going to go up further. So it's something similar. The entire stellar material falls onto this hard degenerate material and then bounces off it at like 10,000 miles per second.
It's a big explosion. There was an online question for the panel regarding the composition. Evan, during your presentation, you talked about the ISM, the gas in the galaxy, the circumgalactic medium, kind of the atmosphere of gas around the galaxy, and then the intergalactic medium, the gas between galaxies. How similar are the composition of those different components in terms of metallicity or the different parts of it? Are they very distinct from each other, or are they basically the same?
Yeah, it's a good question. And yeah, they are very, very different from one another. So typically, gas in the interstellar medium is going to have lots of metals. You of course can find caveats to this, but in general, it's going to be very, very metal rich. And for those that aren't familiar, when we say metals in astronomy, we mean any element that's more massive than helium. And it kind of makes sense when you just think about like the mass fraction of gas in the universe. Like the vast majority of it is hydrogen and helium. But nonetheless, in the ISM, yeah, you're always you very, very often have way, 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 way more metals in the interstellar medium. And then the inverse is true for the intergalactic medium. That material is usually very, 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 very metal poor. As a matter of fact, this is actually one of the conditions that was used to discern between whether or not gas was outflowing versus inflowing into the Milky Way during that plot that I showed earlier. That was one of the considerations that Andy Fox over at Space Telescope Science Institute used to effectively confirm that the infalling gas was coming from the intergalactic medium, was because it had a very high velocity, but also was very metal poor. So not very many metals whatsoever. The CGM is a very interesting mix because you sort of get a mix of both ISM and CGM gas, because you have this infall of IGM material that sort of dilutes the metallicity, but then you have the enrichment coming from these outflows that we keep talking about in the interstellar medium. So what you end up having, and I've literally seen this in my data, you'll have pockets of very metal poor gas that's very likely coming from the intergalactic medium. Then you have pockets of very metal rich gas that's that has very, very high temperature and very, very high metallicity that is very likely is ejected from the interstellar medium. So this is all to say the intergalactic medium, very, very metal poor. The interstellar medium, usually metal rich, and the circumgalactic medium, some complicated mix of the two.
There was a related question, and that was ultimately the stuff that's in a galaxy, the ISM, comes originally either from the stars produced by the stars and the supernovae within the galaxy, or ultimately from the IGM, the stuff in between galaxies. So is there the possibility that nearby galaxies that both came from ultimately the same source material, have similar compositions because of that, because they came from the same stuff?
Yeah, it's a good question. Seems reasonable to me. I think this would so the short answer is very likely yes in the very beginning of that galaxy star formation history, which again is just basically shows how many stars are being formed per time. What I think is also happening too, and so let me just step back. Yes, in the very beginning, they would very likely have similar compositions. But again, since each galaxy sort of evolves on its own terms, they would very likely diverge. What can also happen is the inverse of that, where you have galaxies that enrich the intergalactic medium with gas, where that mass can then, transfer to other galaxies. And we actually have evidence for this because you actually still see metals out in the intergalactic medium that aren't nearby galaxies, that aren't even close to the galaxies in the universe, which is really interesting to think about, because we typically see this in carbon 4, for those curious. And the question is like, where did this mass come from? And the best explanation that we have is coming from, again, these outflows from these galaxies. So did that answer the question?
Yeah.
Yeah, okay.
Other questions? Anybody got anything? And check on the online audience. Okay. Yeah, no, that's good.
I think a couple of years ago, the BICEP 2 experiment initially reported that they found polarizations in the CMB, but it turned out to be intergalactic material. Is that the same as the intergalactic material that we were talking about today?
Good question. My understanding is that was dust in the interstellar medium. Yes, yeah. So they basically didn't account for the dust that was there. This actually kind of gets back to the question I was asked earlier about like assumptions that are made in the data that we have. We have to spend a lot of time trying to remove what we would call contaminants from our data. And in this case, since you're looking for nothing related to the interstellar medium, or our galaxy, then that signal that was coming from dust was absolutely a contaminant, and we take lots and lots of time to remove it in whatever ways that we can. As a matter of fact, that was literally what I was mentioning earlier about Nick going through the, trying to help make this process from going from raw data to usable science data. He's basically trying to get rid of contamination, but not get rid of it enough that he can keep the signal. So all that to say, yeah, no, they're a different thing. That was dust from the interstellar medium.
All right, I got to go on my soapbox here for a minute since this has been brought up. The atmosphere is a great thing for human life, but it really makes astronomy annoying sometimes. End of soapbox, right?
Any additional questions? Kind of at the end of the night. So if there are no other questions, thank you guys for sticking around. Let's thank our speaker and our panel. We, as I mentioned at the beginning, will be back in a month's time on Friday, June 6th to hear all about space weather. That is stuff that's coming off of our sun, both light and radiation, as well as material that can influence the environment and whether or not that makes planets in our solar system habitable for humans and life like us, and what impact that could have for other planetary systems, what their stars are doing. So that should be great from a PhD candidate, Ivy Davis, who's going to give that. And our next Astronomy on Tap will be in a week and a half on May 12th, Monday, May 12th at the Dog House in Old Town, Pasadena, featuring talks about dark matter, some of what we talked about tonight, from Dr. Anna Bonazza, who's at Carnegie Observatories, and from Dr. Gabriele Vahente talking about gravitational waves and what the universe looks like in gravitational waves and what we can learn from LIGO and other experiments that can perceive gravitational waves. So hopefully you'll join for that. And there's pub trivia and live music and all of these things as well. So have a great night, have a great weekend, and we'll see you guys next time.